This lecture is about glaciers and glaciation. So how do glaciers form? Glaciers form when more snow falls in the winter than what melts during the summer. So it needs to be in an area that stays cold enough to maintain snow in the summertime. And then the snow is recrystallized into a much denser mass of small grains called firn. That's similar to if you ever pick up some snow and then squeeze it in your hand to make a really firm snowball. It goes from fluffy snow to more hard, compact snow. So that's a similar concept to when you have deposition of snow over time and then it gets more densely compact and harder. Eventually, when this hardened snow and ice exceeds 50 meters thick, the firn fuses into a solid mass of interlocking ice crystals. And at that point, we pretty much can call that a glacier. So this is a side view of a part of the top of a glacier, and you can see there's layers. And part of the reason we can see individual layers of ice has to do with dust. If there's dust that's blowing around the ground, it gets deposited and then it gets embedded in the glacial ice layers. Also, there may be different conditions that cause some of the ice crystals to be different sizes and things like that. So this is showing you at the top of a glacier, it's basically just loose snow. And there's 90% of this is going to be air, the air in between the snowflakes. And then as you go down into the glacier, the snowflakes are going to get more compacted together. And then further down, they're more compacted together. All the way down here, it's not that much air anymore. You do have air, like little air bubbles within the ice, but it's not like light and fluffy snow. It's hard ice, little bits of air bubbles though. Now this cross section just shows you the typical thickness and age transition of a typical glacier. So as you go down into the ice, at some point here, they're showing you that this level of the glacier is 10,000 years old, 250 meters down. And then 2,000 meters down into the ice, that ice was deposited 130,000 years ago. Okay, and then all this ice was deposited on top of that. So scientists can actually get cores of the ice, right? So you drill down into the ice and you can extract ice that's 10,000 years old, for example. And you take it back to the lab and you go and you can actually extract air from the air bubbles within the ice. And you could analyze that air and determine the composition of that air. And that gives you information about the ancient atmosphere thousands of years ago. And you could read more about that. You could, they explain more about that in this video. You can watch that. So what is a glacier? A glacier is a thick mass of moving ice that originates on land from the accumulation, compaction, and recrystallization of snow. And this is just a photo of a glacier that covers a large area of a continent. So that's Antarctica, by the way. So we call that a continental ice sheet because it's a large, wide, extensive glacier. So where do we find glaciers today? In areas with adequate snowfall and cold enough temperatures to sustain the ice year round. So where do we find areas like this? We find them in high latitude areas. High latitude means close to the North Pole and the South Pole, where the number's closer to zero, closer to 90, right? The equator is 0 and the poles are 90 degrees latitude. So higher latitudes are closer to 90. And your high latitude regions have ice sheets that cover large areas of continents. So again, we call those continental ice sheets. And then your other category of where you find glaciers today is your high elevation areas. And that is because temperature decreases with increasing elevation. So as you go up in elevation or altitude, your temperature gets colder. So generally we're talking about mountains, for example. So mountain ranges are going to allow glaciers to form even in latitudes that would otherwise be warm and wouldn't allow for glaciers. So for example, if you look at the latitude of the Himalayan mountains, that area would not have glaciers because that latitude is too warm. But because the Himalayan mountains are very high, it allows for glaciers to form at that latitude because of the high elevation. So we call those mountain glaciers or valley glaciers or alpine glaciers. So this shows you a distribution of glaciers and ice around the world in the present day. So here are your continental ice sheets. Here's Greenland, Antarctica, and then you have your mountain glaciers, right? So these are this is the Himalayas area, right? And if you go across, you can compare it to the United States and see those are definitely latitudes that are too warm for glaciers. Right, the Andes Mountains, you're gonna have glaciers, the Alps. So here's just a summary of where we find glaciers today. Glaciers are found in areas of high latitude and high elevations. And this is a summary of the different types of glaciers. You have alpine glaciers or valley glaciers or mountain glaciers, pretty interchangeable terms. So those are glaciers that are in mountain valleys, mountainous areas. And you have continental ice sheets. Those are a larger scale than mountain glaciers. They could cover large continental areas, right? Like Antarctica. Now, the continental ice sheets are generally a lot thicker, right? So Greenland and Antarctica are about 3,000 meters thick. Mountain glaciers can be hundreds of meters thick. So there's a vast difference in the thickness and the extent over land, right? This could be an entire continent can be covered by a continental ice sheet. So mountain glaciers are smaller. Now, during the ice ages, which was during the Pleistocene, which began 1.8 million years ago and ended about 10,000 years ago, there were 4 major periods of continental glaciation. And this image shows you the ice sheets in the northern hemisphere during the ice ages. So you can see the extent, this is the United States. You can see the extent of how far south the ice went. Now, we do have a lot of sea ice in the picture. The North Pole does not have a land mass like Antarctica is a land mass on the South Pole and around the South Pole area. But the North Pole, it's sea ice. It's not a continental mass on the North Pole. So the 4 major periods of continental glaciation were the Nebraskan, Kansan, Illinoisan, and Wisconsinan. So those were the major periods of vast amounts of continental glaciation. And in between the glacial periods of the Pleistocene, we had warmer interglacial periods. Now, some of those periods of interglacial climate were warmer than our climate today. Okay, so in between the major periods of glaciation during the ice ages, we did have warmer interglacial periods. And this is just showing you the climate zones during the ice ages. Okay, so this is showing you where the ice was. This is showing you tundra, cold weather conifer forest, temperate deciduous forest was all the way down here. So normally where we are here is a temperate deciduous forest, and your cold weather conifer forest is further up north. So you can see the climate zones were shifted further south. So you had to travel all the way here to get to a temperate deciduous forest, where today that's up here. The global sea level was lower during times of maximum glaciation. Maximum glaciation is referring to when you had your full extent of the glacial period during the Pleistocene. And again, there were 4 major periods of glaciation. Okay. So this is a representation of one of those major glacial periods, and this shows you the full extent of the ice. So during that time period, sea level is lower. The last time we had that maximum glaciation period was about 18,000 to about 20,000 years ago. I have seen sources say 22,000 years ago as well. So this shows you the red line is the coastline of the United States. And well, this is part of North America, right? We have parts of Canada and Mexico in here as well. But I'm just tracing along here, which is the United States. So you're seeing what the coastline was during the ice ages. Okay, so everything within that red line was exposed land. It was not underwater. Okay, so this red dot is showing you New York. So in order to get to the beach, you would have had to drive a lot further, right? You would have had to go all the way to the red line to get to the coast. Okay. Now, a lot of the seawater was held up in the glacial ice. So that's where the water was. It was in the glacial ice, and that's why the sea level was lower. Okay, so how does glacial ice erode land? You have a term called plucking, and that's when glacial ice pulls pieces of rock from the bedrock underneath the ice. Then you have the term abrasion, and that's when bedrock is eroded when rocks and sediments within the ice act like sandpaper and smooth and polish the bedrock surface below the ice. Okay, so you have a block of ice, it's extremely thick and heavy, and it has rocks and sediments in the ice. And when that rubs over the bedrock, it acts like sandpaper and smooths the bedrock out. So here are some terms related to abrasion. Glacial polish, that's when the bedrock's surfaces become smoothed by the abrasion. Glacial striations are parallel scratches or grooves in the bedrock resulting from abrasion. That's from rocks carried in the glacial ice rubbing along the bedrock. It's gonna cause scratches and grooves in that bedrock. Glacial flour is pulverized rock. It's like the dust and it's like a flour consistency, and that comes from the abrasion of rock. So these are all terms related to glacial erosion. And here are some glacial features that we see in New York. This is Central Park. So this is smoothed bedrock, and it has grooves. These are the grooves. This is called Umpire Rock in Central Park. And then on the left, these rocks have glacial striations, just scratches on the surface of these rocks. In this rock here, you have glacial grooves. Here's another photo of Umpire Rock. You could really see those grooves in this smooth rock. And the direction of the grooves, like the way that the grooves are oriented, they're parallel to each other. And then you use the direction to determine the direction that the ice moved. Whether it's like a northwest, southeast orientation or a north-south orientation, it indicates the direction that ice moved. But if it's like a north-south orientation, you need to use other clues to determine if it moved from north to south or south to north. In this case, we know that the ice came from the north and grew southward. But there were other clues we'll get to a little bit later in the lecture. This is a picture of glacial polish, or that smooth bedrock. This is in Orchard Beach. This is more smooth bedrock, or glacial polish. Then we have erosional features and landforms related to glaciation. Continental ice sheets and mountain glaciers. So these details are related to continental ice sheet glaciation and erosional features and landforms related to the continental ice sheets. Areas eroded by continental ice sheets are often left as areas of smooth and rounded bedrock due to abrasion, and we call these ice-scoured plains. And here is a picture showing you an ice-scoured plain. So in these areas, glacial ice has been removed, glacial ice has removed the soil and the sediment that were previously lying on top of the bedrock. So you're left with a lot of exposed bedrock that's smooth and polished. You end up with a lot of wetlands because the glacial ice removes a lot of the sediment, so you're removing the river drainage patterns. So whatever river drainage patterns you had already established in an area get erased, and you end up with deranged drainage pattern. So you end up with a lot of lakes and swamps and marshes. You end up with a lot of exposed bedrock that does not have a lot of soil on it. So you don't really have a lot of vegetation because you don't have thick soil. Also, the area is going to be pretty low relief or flat. Then we have a term roche moutonné. It's also called sculpted bedrock. And when the ice flows over the bedrock, abrasion happens as the ice is moving over. And then you have plucking. So this is going to occur when you have some sort of a little hill. And then the abrasion is affecting the bedrock first. And then as the ice keeps flowing over the land, you have plucking. So what you end up having is a gently sloping area on one side of this bedrock, and then a steeper side on the other side of the bedrock. So here's a photo of the roche moutonné, or the sculpted bedrock. So the glacial ice moved up this side, and that it continued that direction. So when you look at sculpted bedrock, you can determine the direction that the glacial ice flowed. Okay, it's up the gentle side. So ice moved from the gentle side toward the steep side of sculpted bedrock. So that's one of the clues that tells us the direction that the ice moved. And we have valley or mountain glacier erosional features. We're going to talk about all these. Okay, so first you have a river valley. This is a V-shaped river valley, and these are tributaries feeding into that main river. And then you have the ice ages and a glaciation period. All of those valleys fill in with glacial ice, as you see in this picture here. After glaciation, the region now looks very different. And I usually think of this like an ice cream scooper. It's almost like the glacier acted like an ice cream scoop and scooped out the land. So you end up with all these U-shaped valleys throughout the landscape. Okay, it's U-shaped, similar to if you took an ice cream scooper and scooped a valley in a carton of ice cream, it would form a U-shaped circular valley, as opposed to a river, which is a V shape. So U-shaped, right? See, it's all, everything's circular and U-shaped. Okay, and then we have all these little words in here. You have a hanging valley, a horn, a ret, cirque. Okay, so let's go over some of those. Here's the same picture, but more enlarged. And this is another picture from the book showing you an artist representation of these different features. Here's the cirque, a ret, U-shaped valley. So again, the horn, a ret, cirque, and your U-shaped valley. So we'll go over all those terms. So here's your U-shaped glacial valley or trough. That's the general shape that glacial valleys are gonna take because the ice fills the entire glacier, the entire valley. So the ice is able to erode all of the walls of the valley. So here's another picture of a U-shaped valley. Then we have hanging valleys. Hanging valleys form in tributary valleys that lead into a main valley. Often they have a spectacular looking waterfall that the waterfall is usually really tiny compared to the size of the valley. That's usually the characteristic of a hanging valley. A tiny waterfall compared to the size of the valley. So this is Bridal Veil Falls in Yosemite National Park. So let me just go back for a second. I'll show you how this works. So you have this main valley here, but then you have these tributary valleys feeding into that main valley. So you have erosion that cut into all of these tributary valleys, but then you also had the erosion that cut the main valley. So what you end up with is this steep land that goes from this tributary into the main valley. Okay, do you see that? And then you have one over here. So the tributary valley feeds into the main valley. But because of that erosion in the main valley, it causes this steep drop off, and that's your hanging valley. Okay, so all of these steep drop offs are your hanging valleys. So here is a hanging valley in New York. This is Fall Brook in Geneseo. So it's a large, wide area. It's steep, but the water is like a trickle compared to the size of the valley, okay? So when you see a waterfall with a very steep area and like this wide circular cliff with only a little bit of water, that's usually a hanging valley. Okay, an arête is a narrow serrated ridge between two glacial valleys or cirques. Okay, so this narrow serrated edge is an arête. Okay, and then here is an arête as well. All of these sharp looking areas these sharp looking ridges. Those are all arêtes. Okay, so here's the arête right here. Where was I? Okay, so very, very sharp looking. And again, that's between two glacial valleys. So when you look at this, you have this glacial valley here, this glacial valley here, and they were both cut into by glaciers. Or you could think of it like the ice cream scooper, right? So this was scooped out here, this was scooped out here, and then you end up with this sharp ridge in the middle. So the next thing we're going to talk about is the cirque. So the cirque is the circular area at the head of a glacial valley. And it kind of looks like an amphitheater. Okay, so it's like a bowl-shaped depression, like an amphitheater shape. Again, that forms at the head of a valley glacier. Oops. Okay, so you can see these circular areas are cirques. And then we have a horn. This is a famous example of a horn. It's called Matterhorn. It's in Switzerland. And it's like a pyramid shape. And it forms when you have at least 3 cirques. So like one cirque, another cirque, and then another cirque. So at least 3. And it forms a peak that looks like a horn sticking out of the ground. Okay, so like this would be a horn back here. Although we can't see the other side. So maybe look this one over here. It looks more like a horn. Okay, let's look at this one. So you have a cirque here, and it looks like you have a cirque on the other side. So it's like a horn sticking out of the ground. Okay. Okay, so then we have depositional features and landforms related to glaciation. Okay, so we talked about erosional features. Now we're going to talk about depositional features. Keep in mind, most glacial depositional features are related to continental ice sheets, and most glacial erosional features are related to mountain glaciers. Okay, so most of the erosional features we just talked about were related to mountain glaciers. So glaciers push loose sediment like a bulldozer. The result is piles of unsorted sediment composed of a mix of different grain sizes. So a mix of different grain sizes basically is the same thing as unsorted. So glacial drift is a general term for all deposits that result from glacial activity. And we have vast sheets of glacial drift sediments that cover northern United States. So your glacial drift can be divided into 3 categories: till, erratics, which are actually part of till, and outwash deposits. So glacial till is all of the sediment deposited directly by glacial ice. It's poorly sorted, meaning it's a mix of different grain sizes. The sediments are going to be angular, and you're not going to have any layering. It's basically just a pile of different sediments. Okay, so this is glacial till. Glacial till. Glacial erratics are rocks or boulders mainly that are carried by glaciers from a distant source to a new location. So the rock type of the erratic does not match the local bedrock. The erratics were carried there by the glacier from elsewhere. So in this case, you have this metamorphic rock sitting on top of igneous bedrock. Now, when I took the photo, there were leaves everywhere. There's also grass, so you can't see the igneous bedrock, but it is actually all basalt, which is an igneous rock. Okay, so the bedrock in this location is basalt. And then you have this metamorphic boulder just sitting there randomly. So when you see that, just like this random metamorphic rock in an igneous location, that's a glacial erratic. Now the area where it was taken, there was no metamorphism. This is a regional metamorphic rock, okay? There was no regional metamorphism anywhere near this area where this rock was found, which is further evidence that it's a glacial erratic. Okay, here's another glacial erratic. Now this one is really fun. This is called tripod rock. And it's this huge boulder, and it's propped up off the ground by these smaller boulders. So these are all glacial erratics. Now when you imagine glacial ice could be like a mile thick. So it's nothing for the glacier to carry large boulders. And then it's carrying the boulders, and then some of the boulders get dropped out of the glacial ice. In whatever orientation they're dropped in, they're just gonna stay. So this has stayed like this for thousands of years since it was deposited by glacial ice. Here's another glacial erratic. This is actually cracked and not in half, but it has cracked, possibly due to physical weathering related to a tree that was growing out of the rock. The tree is no longer there. So then we have the term moraine. Moraine is the till deposited at the end of a glacier when it is left in linear piles. So here is a glacier, and then you have this line. You would have this line. You can't see the line, but from above it would look like a line. It's just a pile of till at the end of a glacier. And that's your moraine. And moraines generally form when the end of the glacier was stationary for a while. Stationary means that the glacier is not growing and it's not shrinking. It's staying at the same location. And the terminus is just referring to the end of the glacier. Okay, so the glacier, it's more that the glacier is growing and shrinking at the same rate. So you have equilibrium in the glacier. Okay, but the glacier is still moving downhill and still depositing sediment. And then that would form the moraine. So then this is a moraine. This is also a moraine, right? It's just a line that is a pile of sediments. Now, terminal moraines are till deposits that form at the very end of a glacier. So the last glacier advanced as far south as what is now Long Island and Cape Cod. Okay, so let's go back to this diagram here. Okay, we're looking at when we had the maximum amount of glacial ice, how far south did that glacier go? That's what we're talking about. So that's like the lowest limit furthest south. That's the end of the glacier. Okay, so that forms your terminal moraine. And we have that moraine today, we could see it. So here on Long Island, you have this moraine here, and you have this moraine here. Those are actually from two different periods of glaciation that occurred about 10,000 years apart. Okay, so first you had this moraine, and sea level was lower. So the Atlantic Ocean was not over here, right? This was exposed land. So you had this moraine continued across this yellow dashed line over here. Martha's Vineyard, Nantucket, it's all part of the same moraine. Of course, when the sea level rose again, part of that got covered by seawater. Okay, and then you had another glacial period that formed this moraine. And that's Cape Cod. And then the third category of glacial drifts, if you remember back here, till, erratics, and outwash deposits. So here we have outwash. That's our third category. Outwash is sediment deposited by meltwater streams. So when the glacial ice melts, the meltwater forms streams, and the streams deposit sediment. So the sediment, because it's moved by running water, is going to be more like river sediment. So it's going to be rounded, well sorted, and layered. And it's going to form layers of outwash sediment that we call outwash plains. And generally, the meltwater streams are going to be braided rivers. As we learned about in the river chapter, when rivers are overloaded with sediments, they form braided streams. And braided streams are common in areas of glacial meltwater. So we talked about the moraines on Long Island. So now I'm going to show you the outwash plains related to the meltwater that flowed southward from the ends of the glaciers. So here you have this moraine. You had glacial meltwater flowing southward, and it formed braided streams that deposited sediment all along this whole area, and that formed a flat area called the outwash plain. Those sediments are well sorted and rounded. And then you're going to have some outwash plain in between here, because that's another moraine from another glacial period. So you'll have outwash in there as well. This shows you a similar concept, right? You have the further north moraine, which is called the Harbor Hill Moraine. The moraine that's further south is called the Ronkonkoma Moraine. And then south of both moraines is the outwash. And here's a side view, moraine, outwash, moraine, outwash. And this is going across E to F, see E, F, E, F. So what are some other landforms created by continental glaciers? Let's take a look. So here you have the glacier. Here's your outwash. You have a tunnel at the base of this glacier, and this glacier, you have a lake that formed in front of the glacier, which by the way is called a proglacial lake. Proglacial lake. It just means it's in front of the glacier. Proglacial lake. Okay, so this diagram here shows you a whole bunch of different features. You have eskers, kettle lakes, drumlins. Okay, so what is a kettle hole or a kettle lake? These are depressions that formed when a retreating glacier leaves a block of ice that is buried beneath sediments, and then that block of ice melts. So at first you have a block of ice. It gets left behind as a glacier is melting and retreating. And then more sediments are later deposited on top of the ice. And then eventually that ice melts, and the sediments that were deposited on top of the ice are gonna like fall down into this depression. So that's your kettle hole. If the base of the kettle hole is deep enough to reach groundwater, then it will maintain as a lake. But many times they just stay as kettle holes. In this diagram, they're all lakes, but in many cases, they don't stay filled with water. So it would just be a kettle hole. Okay, so here's another diagram showing you blocks of ice left behind in the sediment. And then they get buried in more sediment, right? And then eventually they melt and you get holes in the ground. And here is a kettle lake. Then we have drumlins. Drumlins are elongated hills of till. And then the till gets molded by overlying glacial ice. Usually drumlins are found in groups. So the glacial ice moved over the till and it streamlines it into an oval shape. So this is like the side view of a drumlin. And this is a drumlin that was in Rochester, New York. So this is more of a close-up. You can see it's just a pile of sediment, unsorted sediment, because it's just till. Glacial till. Okay, so here's a picture showing you the ice flowing over the glacial till and streamlining the till into these oval shapes called drumlins. And this is a drumlin field, right? Because I said many times drumlins are located together in groups. Okay, so all these drumlins are parallel to each other. And here is a close-up. And you could see there's a steeper end of the drumlin and a more gentle end. And you know that because of the contour lines. So using drumlins, we can determine the direction that ice moved in this area. because the steep end of the drumlin tells us that that's the direction the ice came from. So the ice goes from the steep part of the drumlin towards the gentle part. Okay, so this is the direction that the ice flowed, from steep to gentle. Okay, and because these are all parallel, you know that the ice flowed generally in the whole area over the same direction. And this is just a picture of an esker. An esker forms within a tunnel at the base of a glacier. Okay, and I showed you a minute ago, you have these tunnels, right? So these tunnels have streams of meltwater passing through the tunnel. And the meltwater in the tunnel is carrying a whole lot of sediment, and the sediments get deposited. So after the glacier melts, you're left with a line of the sediment that was in the tunnel. And those are called eskers. So you see all these tunnels within the ice. After the ice is gone, you see these lines, right? You see those are eskers. It almost looks like an upside down river. Okay, so this is an esker. Eskers are good areas if you're in a gravel business. Eskers are just basically piles of sediment, gravel, and things like that. So you can get the gravel for a gravel business in these types of deposits. Okay, so that concludes the glacier lecture. So I'm going to stop the recording and then show you the video of the glacial ice cores.